All right, today we're going to do something a little different. We're going on an incredible journey to follow a single sound wave from the exact moment it's created all the way to your ear. We're going to uncover the amazing physics that guides it every single step of the way. So let's get into it.
But before we dive in, let me ask you something. What if sound isn't just a thing you hear? What if it's a physical event, something that actually happens and travels through the world, bumping into everything it touches?
Because, well, that's exactly what it is. Sound is a physical journey, and right now we're going to follow that journey together from the very beginning to the very end. Okay, so every journey has a beginning, right? And for sound, it all starts with the absolute origin of every single sound you've ever heard. It all starts with a wobble.
When you really boil it down, sound is just a vibration, a physical disturbance. And crucially, it needs something to travel through, what we call a medium. Could be air, could be water, could be a solid wall. But if you've got no medium, you've got no sound. It's that simple.
And that vibration, that disturbance, it's really just a simple back and forth motion. Now, physicists have a fancier name for it, but for our trip, let's just call it a wobble. Every clap, every word, every single note from a guitar, it all starts because something, somewhere, is wobbling.
So what does this wobble actually look like in action? This classic mass on a spring example is perfect. In step 1, it's just sitting there perfectly happy in its resting spot. Then, step 2, you pull it back and it's just loaded with potential energy. Step 3, you let it go and whoosh, it shoots forward, hitting top speed right as it passes that middle point. And finally, it overshoots, slows down, and gets pulled back again, ready to repeat the whole cycle. That motion, that is the heart of every sound.
Okay, so we've got our wobble. Great. But how does a little back and forth motion here turn into a sound you can hear way over there? Well, that's the next part of our journey, how a wobble becomes a wave.
It's basically a giant chain reaction. Just imagine all the air particles hanging out around our wobbling object. As it moves, it bumps into its closest neighbors. Those neighbors then bump into their neighbors, and so on, passing the energy from that first wobble all the way down the line. The particles themselves don't actually travel very far, but the energy sure does.
Now, this is a really important distinction. When most of us think of a wave, we probably picture shaking a rope up and down, right? That's called a transverse wave. But sound is totally different. It's a longitudinal wave. Think of a slinky. If you push one end, that push travels straight through. The particles get shoved back and forth in the exact same direction the wave is moving.
And that push-pull, that slinky motion, creates this really cool pattern in the air. You get these spots where particles are all bunched up. That's a high-pressure area called the compression. And right after that, you get areas where they're all spread out, a low-pressure area called a rarefaction. A sound wave is literally just this repeating pattern. Squish, stretch, squish, stretch, traveling through the air. All right, our wave is officially on the move. But you know, the real world isn't some empty void. It is full of stuff. And this is where our wave's journey gets really, really interesting, because now it has to meet the world. So, as our little sound wave zips along, it goes on a few different adventures. It can bounce off stuff, that's reflection. It can cleverly bend around obstacles, we call that diffraction. And if the thing making the sound is moving, the wave itself can get squished or stretched out. You've definitely heard that one before. It's the Doppler effect. Let's start with the simplest one, reflection. Our wave is traveling along, and bam, it hits a hard surface, like a wall. It can't go through, so what does it do? It bounces right off. And if you're far enough away for that bounce to take a little time to get back to you, you hear it as an echo. Simple as that.
But what if the wave doesn't hit the wall head-on? What if it just clips the edge of a corner? That is where diffraction comes in, and it is so cool. Sound waves have this amazing ability to literally bend around things. This is the whole reason you can hear someone calling your name from another room, even when you can't see them. The sound waves are bending around that doorway to reach your ears.
Okay, time for our third adventure, and this is one I guarantee every single one of you has experienced. You hear an ambulance coming, the siren pitch is super high, and then as it passes you and drives away, the pitch just drops. That classic neem sound. Why? Why does it do that?
It's all because of the Doppler effect. Check it out. When the ambulance is still, it sends out these nice, even sound waves. But look at step 2. As it races towards you, it's literally catching up to its own sound, squishing the waves together out in front. More waves hitting your ear per second means a higher pitch. Then the moment it passes you, that's step 3, it starts moving away, stretching out the waves behind it. Fewer waves per second, a lower pitch. It's all about that relative motion. So far, we've been following a single, lonely sound wave. But what happens when its path crosses another wave's path? What happens when they collide? Well, you get this amazing piece of physics called interference. And this can play out in two totally opposite ways. On one hand, you've got constructive interference. This is when two waves line up perfectly. Their high-pressure peaks meet, they combine their energy, and the sound gets louder. But if they're perfectly out of sync, if the peak of one wave hits the trough of another, you get destructive interference. They literally cancel each other out, and the sound gets quieter, maybe even disappears entirely. And hey, this isn't just some weird textbook concept, okay? This is the magic behind your noise-canceling headphones. Seriously. They have a tiny microphone that listens to the annoying noise around you, and then they create the exact opposite sound wave inside the headphone. The two waves meet, destroy each other, and you get blissful silence. How incredible is that?
Okay, we followed our wave all over the place. We've seen it bounce, bend, and even collide with other waves. For our final section, let's rewind, let's go all the way back to the start, and look a little closer at how that initial wobble even gets made in the first place.
Here's the big secret. Every single thing that makes a sound is just a machine designed to create a very specific kind of wobble. A guitar string, a giant speaker cone, even your own vocal cords, they're all just different kinds of wobble makers. And how you make that wobble? Well, it matters a lot. This chart shows something really interesting. If you have a source that just pulses outward in every direction, like an expanding balloon, it's super efficient to creating those big, booming, low-frequency sounds. But if your source just wiggles back and forth, it's actually pretty bad at it, especially with those low notes. So the shape of the wobble directly controls the power and character of the sound you get. And just like that, our waves journey is complete. We started with just a tiny wobble. We watched it grow into a wave of pressure, and we followed it as it bounced off walls, bent around corners, and even fought with other waves. And the amazing thing is, by understanding these really simple rules, we can actually control and shape our entire acoustic world.
So, I'll leave you with this. You now know the fundamental rules of the game. You know how sound is born, how it travels, and how it behaves. The only question left is, now that you know the rules, what new sounds could you create? What kind of acoustic worlds could you build?